industry, and the big bets the whole industry is making is this, right? If we collect enough human data, or if we bake enough human priors into these models, and the robot or the machines will eventually do what we do and beyond. So this is a very powerful bet and has produced lots of exciting research and outcomes. And for example, all these large language models or vision language models have produced so many possibilities that we haven't been able to see before. And if we translate this into robotics right now, you will see people start to collect lots of robot data, and almost sort of having human to behave like a robot, right? So in this case, a human can use a VR interface to teleoperate a robot to collect more data. In other cases, people can develop wearable data sensors that put on human body, and then while humans are imitating, if they are the robot, they can collect the data for training the robots. And this sort of have a big assumption behind this, where the assumption is we think the human data and the robot data will have a strong overlapping, which means that wherever we want to deploy the robots to, we need to have the access to the human data, or to some extent. But today I would like to make a different bet, which is how do we actually get robots to learn this by themselves? And this is come back to the theme of my lab. My lab's research is focusing on building the machines that actually discover, or discovery machines that is able to understand, perceive the environment, discover how the environment works, how the physics works, and even how their body works in the environment, and practice all the skills along the way while they're acquiring new knowledge, and eventually being able to even do things beyond what humans can do. And I think that's kind of the key catch here is if we purely rely on lots of human data or human demonstrations, whereas if we want to deploy the robots to cases where humans are not very good at, and in fact, even though in the current state of the art approaches, we still have to train humans to be a good data collector for the robots, then having machines to be able to discover all these things on their own, having them to explore this and build their own internal understanding of this, and have a coherent and consistent understanding of the world will get us to go a long way. So have a high-level overview of what we want to build as the key vision in my lab is we want to build machines that can discover how the world works on their own, but of course with minimum human supervision, eventually work well still with humans and under human guidance. So some of the examples, starting from how the machines is able to perceive the environment. If you go to the San Francisco area, you're going to see lots of self-driving cars. And most of these modern robots we see heavily relies on camera sensors, where you have LiDARs or RGB or depth cameras. If you look at humans and animals, we actually rely on a lot more other sensing modalities. This is mainly because if we cannot perceive the environment in a comprehensive way, we may make wrong decisions. So my lab has been looking at some of these recent other possibilities of expanding the perception capability of machines. So on the left, you see here is a sensor that we built, we call it sensory, where we gather all the gas sensors and VOC sensors that can detect the small air particles emitted by fungal modes. And in about 3 seconds, we can tell you the species of the fungal mode. In about 7 seconds, we can tell you the distance away from the fungal mode to the sensor. And the way this works is that we can have a robot to autonomously explore the environment and train themselves to gather data for themselves. And once you have the model trained, you can deploy the sensor to the robot. And we actually right now have a robot running around in home to tell you where the fungal mode could be, and we're further scaling this up. Another example on the right here is a robot hand that has vibration sensors in the fingertip. So different from the typical robot hand where you need to rely on a vision camera to tell you where the objects are, this hand works by randomly exploring the environment and tap things around. So the sensors embedded in the fingertip of the robot only sense physical vibrations when there's a contact happened, and it does not really transmit sound as we're speaking now. And these are very cheap sensors you can get online easily. These are the same sensors you get by recording sound from guitar from Amazon. And but by equipping them on the robot hand, coupled with the machine learning algorithm, we can get to the level of with about 4 times of tapping around an unknown object. We can tell you the 3D point cloud of that object, or we can tell you the per pixel level of material composition of that object. For example, it could be one part of the finger touches the rubber part of a hammer, and the other part is a metal part of the tool. And you can do more even crazy and interesting things. For example, what we did was put dices into a container, and when you shake around the container, we can tell the number of edges the dice had, or the number of dices we put into the container. Once you have all the sensing modalities, at the bottom, we show a case where you can have a robot to be equipped with vibration sensors on their leg and foot contact sensors at its bottom, and also having the LiDAR sensor and the camera sensor all fusing signals in the wild environment. So this is actually in Duke Forest. We can have the robot dock to, while it's tapping on the ground, walking, you actually transmit the vibrations. You're tapping on different textures of the ground to the robot body, and you fuse all the sensing signals to have a complete 3D understanding of the world for you to make better decisions. In this case, the robot can make a safer path or a planned path that can save more energy. Once you sense the environment, we also have been looking at how you can truly adapt the policy or the control of the robots to be adaptive and more fluid in this kind of ever-changing environment. So, of course, you have seen all this amazing progress we've made on humanoid robots. And just in last year, we've built our own Duke Humanoid V1, and we're actually baking Duke Humanoid V2. We make the entire hardware and software open source. So has been already people started replicate our design. But moreover, we want to see how we can autonomously even design these robots based on different tasks or different environments. On the left is an example where a paper will come out soon on this to see how we can look at the fundamental physical principle of the nature, which is symmetry, and what happens if we push symmetry, especially dynamic symmetry, to extreme. So this is a robot we call Argus. It has 20 legs and 20 cameras within each of the foot node. And this robot was designed based on that fundamental principle and theoretical derivations about why this type of robots actually performs well in omnidirectional movements. And it's really able to do lots of amazing things. It can move around around the Duke campus. We bring this to the conservation area. It still walks on a beach area. It can also climb between parallel walls under lunar gravity, and it's able to follow different objects, even manipulate objects on the ground while it is maintaining its stable locomotion. On the top right side, you see an example where you have the robots to the only thing that a user type into the system is a sentence about what you want a robot to look like and what you want it to optimize for. For example, you may want a robot to walk as fast as possible, or you want a robot to walk but being able to save energy. So we designed a system called a text robot to convert natural language from human instructions directly to a functional physical robot that directly walk out of your 3D printer. So it takes about several hours to evolve its body, generate different possible hypotheses of what the body might look like. You may actually swap your body parts with other variations. And out of thousands of variations and several iterations of this evolution, the robot simultaneously train a walking motion for the robot, and eventually you get a robot they can put together with about 10 minutes, and the robot will be able to walk out of the 3D printer. And of course, looking at beyond the body, the robot also have to be able to perceive the environment changes and react to these things. So on the left, we had a system with about 80 seconds of data in total, both in simulation and the real world. And that means about 10 seconds of real world data, we can directly fly a palm-sized drone in the real world to track a circle, or in this case, in the bottom case, you can drive a 1/10 of a F1 racing car, also with about 10 seconds of data to truly adapt from a low fidelity simulation to high fidelity controller. All the way to things where imagine a case can robots swap their policies and their skills with other robots where even they have different bodies, to cases where we can use large language models to help us to design better principles to training the robots and better and faster than cases where human engineers can imagine. And of course, machines are not going to work alone, right? So my lab has been pursuing lots of studies on how we can have machines and AI coexist, and especially how machines is able to learn under human guidance. And so on the left is a system that we have developed in the past few years where you can have a single human to watch an AI agent to learn a new task, but humans are providing high-level guidance and feedback. For example, clicking on buttons to say you're doing a great job or bad job, or just by having your mouse up and down to give different sort of reward values to encourage agents to learn the agents faster and the skills faster and better. Two cases on the top right you see is an instance where a single human can guide a team of three robots to play hide and seek. In this case, they're guiding a team of secret agents to catch the hider agents in green color to where even the green color agents actually moves faster and have better perception capability than them. And this is touching on the fundamental capability of cognition in human brain, where we can infer what other agents are thinking and even how the world looks like from their perspective, what we call a theory of mind capability. And more recently, we've been getting more excited about looking at how we can have minimum number of humans to optimize workflows of heterogeneous of agents in a maximized number of AI agents. So in this case, we are able to achieve a single human to guide 20 to 50 AI agents to perform a very complex task, for example, in wildfire response. So this kind of give a brief overview of what we mean by machines being able to discover what the environment kind of looks like through multiple different sensing modalities, to machines discover what their body even looks like on their own, to even adapt their body and design their body to adapt an environment, all the way to figure out how other machines or humans work, and by discovering this knowledge to work with them. But today, my focus is going to be talking a little bit about how the same idea of discovery machines can help us even uncover novel scientific principles and discover, scientific knowledge from data alone. So let's get started on a very simple example that if any one of you have ever taken, physics or mechanics courses, this is pretty much the first example you're going to see, right? So what you see is a single pendulum. And what the textbook typically opens up is to say, let's find out how to define the variables of the system, right? So people are going to say, let's draw a line from the bar of the pendulum, and this is the angle of where the pendulum is swinging. And then how fast it is going through the angle is a angular velocity, right? So it's the derivative of the position. So it's describing how fast you're swinging there. And typically, this is something we call a two-dimensional system, which means that we just need two variables to describe the full dynamics of the system. If you only have the angle, that cannot describe the full dynamics because I can swing that with a relatively faster speed or with a very relatively slow speed. But once I know both the angle and angular velocity of the pendulum, then I can characterize the system dynamics in an accurate way. And once you can write down the variables, simply based on F equals ma, you can derive the dynamics of the system, right? So as we have here is the physical equation. And this process basically maps to almost all of our recent discoveries and concrete physics discoveries especially from dynamical systems. And a dynamical system is a very general system that anything that changes with time is a dynamical system. So this is great, right? Why do we still want to, what else do we need? It turns out we can already do a lot of things with this. In 2009, there was a paper that actually came from my PhD lab where people discover a principle that you can gather this variable data. For example, a double pendulum will become a four-dimensional system, right? So you have the angle and angular velocity for both arms. And it's a chaotic system, which means that if humans look at the motion of the double pendulum, we cannot accurately predict what will be the next state of it, right? It's very hard for us to predict what happens next. But if we have these variables from the angle and angular velocity of the arms, what you get is kind of a plot in between, right? And this paper basically presented an evolutionary algorithm, and it later on triggered a software called Eureka that is able to get from this time series data to extract fundamental governing equations of the system. So what you see on the right side is the discovered invariance of the system that can, discover the Hamiltonian energy of the system, and this whole system equation describe the physics of this. So it's really powerful. People have been using this for many, many years. But it's no longer open source anymore and hasn't been upgraded to the modern hardware. So in the past year, my lab has been looking at how we can even gather these variables and update the previous Eureka software and further open source this to the community. So now if you have a set of variable data from time series data, you can download our software. This is what we call Semantica that can basically look at how different variables are correlating with each other and try different combinations of equations coupled with different mathematical operators in a thorough evolution algorithm, and by finding most frequent sub-equations, sub-expressions to help speed up the searching process, you can end up with even better accuracy and even faster recovery of the system. So we're able to recover more than 100 of dynamical systems equations from the benchmark data set, and even be able to recover new equations that were possible from the previous work. And moving on, if we look at vast majority of the dynamical system, right? So this can ranges from mechanical systems like pendulum to electric signal systems to even neuroscience data with the a neuroscience model about how neurons sort of work out to weather data, to climate data, to energy systems. You have basically all of these are dynamical system, right? And in particular, what we can do is by gathering all these variables data. Now, if we marry them with more than deep learning, the hypothesis in sort of the dynamical system world is that if you have infinite dimension to grow this variable, you would be able to end up with a linear system. So this is a theory that has been very well known in dynamical system theory called Koopman theory. But of course, we don't have infinite dimension, right? But we would still like to convert some of this highly nonlinear system into a linear representation. This is in particular because we have a lot more mathematical tools to describe a linear system, but we have very limited knowledge about how to analyze a nonlinear system. So it turns out we were able to gather all this sort of variable data that predefined by the humans and scientists and get the time series data. And we can bake this sort of prior knowledge. We would like this deep learning model to show up as a linear system. And we can discover, lots of fundamental principles from this, right? So this is sort of, you can look at, even translate this to a real world system. And we were able to discover even lower dimension of linear representations from the highly nonlinear system. So this was quite a breakthrough to us where we can not only discover the linear representations of the system from nonlinear systems, but even lower dimension representations of that. And it translated directly also to the same case where I showed a neuroscience data with a Hodgkin-Huxley model that even won a Nobel Prize in the last century. We were able to discover a linear representation of that system. And from there, we have a lot to know, right? If you open up any linear system textbook, we can tell when the system becomes stable. We can tell when the system become chaotic and had a transition. We have knowledge about how the system is going to behave under equilibrium states. So we have a lot more to say there. And that's kind of a lot of things we can already do if we know all these variables. And so here we showed examples where not only you can discover and interpret what the system actually tells you, you can predict what the system look like. So this is from a 96 dimensional climate data. On the left is the ground truth of the what the variables might look like. On the right side, we were able to predict how the system evolves in the future by recovering a 14-dimensional system from this 96-dimensional system, and it's in a linear representation, right? So you can see this simplified system even tells you more and it give you a pretty accurate prediction of the future evolution of the system. But let's go back to this example. And here's the catch. The catch is, in fact, there are more than one way, and if not infinite ways of describing the same system, even with a single pendulum, without using these two variables. And in fact, it always has to be two variables because this is a two-dimensional system. But it could be kinetic energy and potential energy. In fact, this definition of angle and angular velocity are human-defined concepts, right? These are simply things that we draw and we think this is measurable and we name this as a variable at, for example, angle. And these are human-invented concepts. But in fact, I started to wonder why angles are not decided or defined by the 2 to the power of sine of theta. Why it has to be this particular number, right? And like I said, there are actually in theoretical math, any definition of the dynamical system has much more than one, sometimes infinite, if not many of different ways of defining the same system. It always has to be these two numbers. And if we step back, one step back from this discovery process of trying to understand a dynamical system, there's been tremendous progress we've made on building better models to describe the system, even including some of our previous work that talk about how do I discover better equations, writing on the ODE or PDEs to describe the system. And there's also been lots of progress we've made on deriving the solutions for the system, right? So we have set of equations, we have lots of ways to accelerate the computation and while balancing the accuracy. But there's always a one fundamental assumption. That is, we always know what are these corresponding state variables. We are given the angle and angular velocity. And almost when even I have to admit, when I first take these mechanics courses, I just didn't doubt about why we're given angle and angular velocity and why do we even start it there, right? So we always are given the sentence say, given this as the variable, the angle, and given the derivative of the variable of the angle will become the angular velocity. Now, if we follow Newton physics law, here is the dynamics equation we can derive by conducting force analysis. So if this is still not clear to you why this is very important, let's look at a system like this. This is a combustion system, right? It's a fire. This is a real fire recording. What are the angular velocity that we can define here? And if this is the only thing you're given, right, how can we understand and mathematically model the system? And in fact, we still do not have a Garvin equation that we can confidently write down to describe a system like this. So we simply don't know even what the variables are. And this fundamentally limits our capability of interpreting and understanding lots of complex data. So what we would like to do is to even figure out in the first place the dimensionality of the system, right? It's very straightforward to see a single pendulum is a two-dimensional system, a double pendulum is a four-dimensional system. But for a fire, even what is the dimensionality of the system? And can we discover this autonomously? And even can we even tell the values of what these variables could be? And it may or may not necessarily be the angular velocity. So what we did was we, as many people have been already familiar now, deep learning has served as a very good compression model where you can train something called an autoencoder that takes in video frames from the past and predict the future video frames. And the way you train these models is that you have to compress the high-dimensional image representations into something much lower dimension, and then you deproject these representations to a higher dimensional and recover the original frame. So this kind of autoencoder framework has been pretty powerful. But when people design these kind of systems, the dimensionality of this latent bottleneck, right? After you compress everything from the encoder and before you decode them, this is where you get the lowest possible dimensional representation. And this number typically are defined in a very empirical manner, right? And computer scientists really like the power of two. So the way people deal with this number is like maybe throw in an arbitrary number. For example, I can take 512 or 1024 as the dimensionality. And if it works, that's great. We're done. But if our goal is to find out the minimum dimension that we need to use to describe this system, you can imagine we need to shrink the size of the latent dimensional vector once the system breaks, right? Because if we're able to predict the future frames accurately, this means that this compressed blue vector here has to have all the information necessary for me to predict the future. And if I can compress that dimensionality to its lowest dimension, then we're done. We find the dimensionality. But in practice, this is impossible because when you train these deep neural networks, you have to balance between the optimization accuracy at the same time the difficulty of forcing the model to make predictions based on minimum information. So the first contribution we did was we found that there has been a lot of studies in the past, especially in the past 10, 20 years in statistical learning, where people kind of look at a high-dimensional manifold and look at the dimensionality of the manifold through statistical methods. And in this case, what we found is that if you project a relatively high-dimensional vector, for example, 1024, and if you treat every single one of these high-dimensional vector as a data point in n-dimensional space, you randomly start from one point, you grow an n-dimensional unit volume sphere, the number of points you can cover within that unit volume sphere will indicate the dimensionality of the system. And just by using this existing intuition, on this the compressed encoded representation from this, we were able to calculate the exact intrinsic dimension of the system. So intrinsic dimension here will correspond to the minimum number of variables you needed to describe the full dynamics of the system. And in particular, in our paper, we have a set of algorithms that we tried, and it all kind of worked pretty well. But the most robust one is this Levina-Bickel algorithm published in 2006. So now that we have the variables, right, on the left side of each pair are the real videos from the original recording. So these are ground truth systems. On the right side of each pair, these are predictions coming from this autoencoder. So this means that we are able to predict the future video frames pretty accurately. The numbers on the right side pair are the estimated number purely estimated from the video frame, right? So there's no prior baked-in physics knowledge. We actually don't know even what the system is. It's a mechanical system. It's like the bottom one is a lava lump, or an air denser or a fire system. We're able to recover the dimensionality. So it's fairly accurate for a system that we know. But there are systems that we don't know, right? So like air denser, lava lump, or fire systems, like we just actually still don't know the true dimensionality of the systems. But as the system get more and more complex, our dimensionality also becomes higher and higher from the estimation. Now that we have the dimensionality, right, the second stage we have to go through is to take this compressed vector, and now we want to find the variables. Because the first step only tells me the specific dimension, but remember the blue vector is still with pretty high dimension, right? So even the original one has millions of dimensions from all the pixels. The blue one has 1,000 dimension, but this is a double pendulum. So we know that the true dimensionality is 4. So how do we find out what these 4 variables are, and what these 4 variables the model is using to learn to capture the full dynamics of it? So we bring a second stage where we train a second neural network that takes in this blue vector and try to reconstruct it. But now we can constrain the latent bottleneck of the autoencoder to be the exact dimension of what we discovered, right? So now we know this is the 4-dimensional system from the previous step. Now we'll plug in and making sure the full dimensionality will just be 4. So now if the whole system is able to go through from this frames all the way to the blue vector, send into the second network, and go through this bottleneck that only reduce this to 4 numbers, and all the way upscale, and going back to the decoder to generate new video frames, we essentially find out what these variables are. And this is what we termed as neural state variables, right? So the angle velocities are typically defined as state variables in dynamical systems. And the one we use neural network to find them out, we just simply call them neural state variables. So it turns out this is a very powerful paradigm, right? So if you look at some of the generative AI video generations, this is what you see on each pair on the left, right? So videos, you may see new object suddenly shows up, or just by rolling out the future predictions for less than a minute, you see some of the objects sort of disappear or objects get distorted. On the right side are predictions done again by rolling out 60 to 100 times in the future. We can have video predictions still maintain the physical property, right? So it understands that the pendulum cannot change its shape. The physics also needs to be accurate. So simply bringing the dimensionality down to the exact intrinsic dimension of the system and forcing the neural network to make that prediction through that bottleneck, we're able to get much more accurate long-term predictions. And several other free sort of properties you can get also includes robustness, right? So on the left, we see is if we're training the model on a clean data set with this kind of yellowish, grayish background, and now if you put perturbations on it, for example, you can have small occlusions on it, you can cover part of the background, or you throw a bunch of white noises onto the image frames. And if you're simply using the model to predict what's coming next, just for the next 2 frames, right? The delta t here is 1/60. So it's very, very small delta t. This model immediately breaks, right? And this is actually a pretty powerful model that has 8,000 dimensions in its latent space. And it can predict the next frame perfectly until you put a very small perturbations on top of that. Whereas our method that you can force the network to go through this low dimensional bottleneck, you get this almost perfect prediction that matches with the ground truth. Now, if you send these predicted frames as the input for the next iteration of prediction, then this is how you can generate clean and long-term predictions. So this is where things becomes really powerful. But here's the catch. My struggle after I finished this work was I really want to understand what this variable actually means. Because obviously, for a single pendulum, double pendulum, or these, other complex systems, you give me the same dimension as human-defined systems, but the values of these variables are not corresponding to the same variables as human-defined, right? They're not strictly one-to-one corresponding to the angle or angular velocity, or not anything simple transformations of those things. And this is the part of the deep neural network, right? If for any one of you have trained neural networks, if you use a different random seed to train the network, you may end up pretty good results all the time. But the representations you learn are actually quite different. So this is a visualization of this two-dimensional vectors discovered by our model from the single pendulum, and the colors are indicated by the values of the human-defined variables, right? So I believe in this case we're coloring this based on the angle. So you can see this sort of forms some clusters in this case, and it's kind of a very nice heart shape. You run the model again, this is what you get, right? You actually get a system that looks very different from the previous ones. They all can do well on all the examples that I've shown before. And to validate the system, we actually train hundreds of different models under 9 different data sets. But you end up with very different representations, even though they perform well. And they correspond nothing to a human-defined physics language. And if we ever want to go a step further, meaning not only telling me the dimensionality of the system, and not only telling me finding the values of these variables. These are a cool first step. But if you ever want to analyze the system, or I want to control the system, I need to make sure that I can do things with these variables. I want to make sure that I can understand these variables. I want to make sure I can operate on top of these variables and connect that with the textbook knowledge we have learned from human scientists' discoveries about dynamics, about control, about data analysis. So how do we deal with that? It turns out it's impossible back then. When we just extract variables, I still remember I had these hundreds of pages of PDF that I try to find the relationship between these machine-discovered variables versus the human-defined variables. And here's one of that hundreds of PDFs. And if you see the issue here is that this looks nothing like human-defined variables, right? If you still remember this sine wave type of plots that I showed earlier for this double pendulum recording, there's one fundamental capability that we simply do not have, which is there's no such sudden jumps in the variables that a human define, right? So you see this kind of variable. At one time, it was a pretty low value of the angle, and just next to it, the variable becomes a very high value of the theta. And when this kind of jumps happens, the value itself is fine, but what's not fine is that we cannot actually run calculus on it, because the fundamental property of anything we can run calculus on top of the variables with respect to time is that it has to be smooth with respect to time. And just because this discontinuity that we have along different paths, and especially when we go even with higher order variables, like the first order variables here with velocity, this kind of sudden jumps and noises points shows up everywhere. So it's nothing like any variables that a human kind of defined. And that is the reason why you see this discontinuity of the physical variables. So let's take a step back and just think about what could we do if we actually have a smooth variable as how human defined this. So it turns out we can do a lot of things. This is a single pendulum, right? The numbers here shows up the angle, and they're all smooth, right? With respect to time, you don't see an angle of a pendulum change from 30 degree, and next time step it suddenly shows up like a negative 60 degree, right? So it's going to be changing gradually around that region. If we do have these variables, the number one thing we can do is we can write down an equation, right? So here is the dynamical system equation we can write down to describe the dynamics. And second, we can look at something called vector field here, which tells me based on these two variables, I can tell you when the system becomes stable, right? So here around this red circle here, this is when the system becomes stable around it. And furthermore, I can tell you the governing frequency of the system. And I know we know a lot of things about how to deal with the system. And the challenge here is how do we connect these discrete variables to this human-defined knowledge? We can understand the system and get equations, get vector field, understand equilibrium of the systems, the stability of the system, characterize the chaotic behavior of the system, understand the governing frequency of that. If we stop there, we just cannot do any of these things. So what's needed is not just a full description of the system dynamics to have that variables we discovered to be compact. The second very important property we would like the variables to have is operability. Can we use mathematical tools such as calculus to extract scientific knowledge from these variables? So both compact and operable variables are very important properties to really get us to the next step. So this is how we kind of look at how we can extract these operable variables from videos, right? So the way you do this is that, okay, we have these video frames, and then every time step we advance by delta t to get the next time frame. And this is a perfect case if we have these kind of variables, if these variables are smooth, then we will be able to get this equation here, right? We can write down the variable is the v, and then the v dot equals f of v, right? This is the most simplest form of representation of dynamical systems, and we can use this to represent all these dynamical systems in this way. But here is the what originally, if you look at one single trajectory, right, what it looks like is that you have the initial video frames, you comprise it through the first stage of the model, and then once you extract these relatively low dimensional vectors like 1,000 or 8,000, you send them into the compression model. You force the bottleneck of that model to be equal to the dimensionality you discovered from the first work. And then you would hope you could get a smooth trajectory like this. But what you end up with is a trajectory look like this, right? So if you follow every single time step and you plot these variables you get from them in this 2D space, for a single pendulum, you actually have this sudden jump from one point to another. And there's no smoothness that you can talk about there, and there's no way you can do any meaningful gradients information from it. So the second work what we did was to add in the smoothness constraints. So I'll skip the math there, but the way we do with this is to ensure that if the variables are close by in physical time, in the physical space, for example, adjacent video frames, we also enforce these two variables stay closer within the video frame, or within the projected latent space or discovered near state variable space. And now that if we can enforce that constraint, it would basically refine these variables from from near state variables to something we call a smooth near state variables. And this is what end up with as the same trajectory being run, but now we were able to get a trajectory like this from right to left. So here is a further illustration of what this means. If you just rely on the first model, right, you discover the variables and they're not smooth. If you plot them, this is what these plots look like. And if you calculate the vector field of these variables, this is what you end up with, right? So these are the things that actually doesn't really tell anything, a pattern. You cannot really extract any meaningful information from the gradient field. It's pretty messy and very noisy. Once you enforce the smoothness constraints in them, this is what you end up with, right? So you have much smoother variables discovered, again, solely based on a input video, right? There's no other things we're enforcing here other than this very fundamental property of mathematical variables to run calculus on, which is smoothness. You end up with the smooth variables in time series data, and now you can calculate very smooth and meaningful vector field. And this goes from a simple spring mass system to a single pendulum to a chaotic system like a double pendulum to a fluid system here as the cylinder wake system. So now once we have this, so next I'm going to show you a little bit some of the examples of what we can do with discovered smooth variables. First, of course, you can discover the equilibrium identification. You can identify what the system will look like if the system becomes stable. You can analyze when the system becomes a chaotic system and whether the system is in a chaotic phase or it's actually in a periodic phase without getting into that chaotic phase yet. If you're in a fluid systems, you can perform limit cycle detection. You can analyze if there are periodic behavior when the system become bifurcated, and you can detect the vertex shedding changes, all the way to even generating and synthesize new data, but now following the exact physics law governing principles. So this is very straightforward. Once you have that smooth vector field, you simply just making sure you want to find out when that vector field equals zero. That means the system no longer changes, right? So this is what the system actually just find out. On the left side, this is what we show from the original video that has no states that corresponds to this at all. So in the original video data sets, all of these pendulums are actually moving around continuously, so it never has a example to show what the system look like when it becomes arrives at an equilibrium state. We're able to tell you that this is what the system will look like when it becomes arrive at this particular equilibrium state. And further, you can use the decoder to render data to show me what it looks like. And moreover, you can go from the point you discovered with the equilibrium states and continuously find out the trajectory is rounded and move further and further away from it, and then generates videos to tell me what the system might look like if I gradually move further away from that equilibrium states. And here is different plots you see. And while you're moving away from it, actually the pendulum moves, swing larger and larger with its maximum angle. And now, because we have this, vector states, we can then derive the governing frequency. So here is a governing frequency we discovered from this video data set. We think we estimated the governing frequency is about a 5.16. And if we actually go take human efforts and label the angles and angular velocities by hand and derive this based on the known equations we have about the data, right? Remember, our method does not have that information at all, but only a video, you are able to get a accurate governing frequency, which is 5.43. So, which is pretty close from what we discovered. And you can do the same thing, right? Apply to all these four systems going from the periodic system to chaotic system to fluid systems. We can discover all these sort of frequencies up in the first row, and then the governing frequencies of this is the spring mass, right? This is the single pendulum, and this is the double pendulum estimation. So it's all actually very accurate, reflecting that. And in the double pendulum, you actually have two governing frequencies, and so we're able to recover both of them. And moreover, for the system, for even for double pendulum, even though it's a chaotic system, it doesn't always stay as a chaotic behaviors, right? So we can quantify this. For example, you can count the percentage of the state space visited by this trajectory, and you can see how the trajectory diverge once, even though you started with something at the beginning very similar, close by initial states. How much do they diverge? Become very different in the future, and especially when you have a chaotic system when you slightly perturb the initial states, you will end up very different trajectories in the future. And that's kind of a property of a chaotic system. So from these two things, you can tell when the system becomes chaotic. And of course, you can measure the distance because we can identify the stable equilibrium of the system. For any given trajectory, we can measure the state distance to that identified state equilibrium from the discovered variable space. So this is a regular behavior. And again, these videos are not picked by me, right? So this is based on us having defined this metrics and calculate these quantities in from the discovered variables. And then we found out these ones that fulfill these conditions and render the video. So you can see these are regular behaviors. The models actually, the pendulum, even though they start roughly similar at the beginning, it doesn't really diverge too much in the end. And the distance was quite narrow in terms of its distance away from the equilibrium state. Once these numbers becomes really high, right, you have much larger distance all the way to the right, or the divergence rate becomes much higher, and it never actually comes back to the original state. Then this is where you see, even though they start very, very close at the beginning, I'll play the video again, right? These two states are very, very close. But once you start to release them, they end up very different ones. And again, I actually have this pendulum right behind me. This is a real physical pendulum, right? This is a recording that I use iPhone to record a video from my phone. This is not a simulation. And you can do the same thing. right? So the top trajectories are using our method with a simple k-means clustering, you can find out what are the trajectories that are more regular trajectories and what are the trajectories that are more chaotic trajectories. And now I'm playing the video, you're going to see the first row will exhibit this kind of periodic behaviors versus the bottom ones are kind of going with the crazy trajectories with as the chaotic trajectories. And so, moreover, for fluid systems, you can detect the limit cycles, right? From when I play the video, you will be able to see the discovered variables now shows the exact same sort of limit cycle behaviors as what it corresponds to see from the video side, right? So you see the beginning, and then now it's have this kind of limit cycle bouncing behaviors, and you're going to see the same behavior shows up in the discovered variables. And of course, if you have this with different kind of read-known numbers, you're going to be able to detect the system bifurcation that goes from laminar steady wake to periodic vertex shedding. And moreover, you can generate new data because the original data set we had was only synthesized with or recorded with 60 FPS. Now, if you want to have a super resolution with respect to time, so because now you have the exact equation, the vector field, you can just increase the delta t by having, reduce the delta t by going with 10 times more sampling in time. So on the left is the original video data set we had. And on the right side is the 600 FPS video synthesized by going from that equation all the way to generate the using the decoder to generate the real data. So you have a super resolution data in this case. Now, because you have that equation again, you can add damping factors. You can tell how much damping factor you want to add in there. So on the left is a damped behavior. On the undamped behavior, the original data. On the right side is I can control how much damping factor I want you to generate the data. So this is in contrast with the state-of-the-art generative model, we're seeing that actually doesn't generate data that follow physics. In this case, we are using the discovered physics to control how the data can be generated. So with all of this, it kind of covered this piece of information I'd like to share is machines actually can discover these variables very well. And but the way to do this may not actually have to go through human-defined variables. If we actually let machines to discover this knowledge and raw knowledge automatically from the videos, and if we want a machine to help us discover new scientific knowledge, perhaps we should let them to discover their own language for science. And the next job for us is how do we actually distill this knowledge from this vast amount of knowledge and abstract knowledge discovered by a machine and almost interpret that language spoken by the machines to human understandable and operable scientific principles to share with the scientists. And I do think this closed loop collaboration between the human scientist and machine scientists sort of work together will be able to form an iterative and faster iterative loop to help us to understand more and more data that we are gathering right now, but we don't understand. Thank you.